NASA, the Science Mission Directorate and the Department of Education had a combined call for proposals to give students participate in the development of instrumentation for science. And the projects could either be instrumentation development only or both development and science application. And as part of that, they had a certain amount of money for lots of universities and different types of science that NASA supports to go out and submit to this call. And we decided to leverage our expertise here at the University of Oklahoma in meteorology and radar development to go and build a radar that we could fly on one of NASA's platforms and sample some weather. So as part of that, the Advanced Radar Research Center worked on the development side. So they're going to have a team of undergraduate students developing a cloud radar that we can put onto an aircraft. It's the size of a shoebox. Okay, so it's a very small radar, very lightweight. Most radars that have been adapted to aircraft in the past have been much larger, heavier, much more expensive. We can build this radar for about $50,000, give or take, depending on the capabilities that we want to put into it. It's a much lower power radar than traditional radars on aircraft systems. It can't see as far, but we can still do a lot of science with that. And ultimately, building a small radar like this will enable it to be placed on a wide variety of aircraft, from the really large research aircraft that NASA flies, big cargo planes, to the really high altitude aircraft like the NASA ER-2, which has a pilot sitting in the cockpit wearing a flight suit, and it goes and flies around for 10 or 12 hours around the country. Or in the new sort of addition to the NASA fleet, the Global Hawk, which is an unmanned system. It was traditionally a defense system, so a retired military drone that they basically gutted all the sensitive military capabilities out of there and put a whole bunch of science instrumentation in there, so they can measure trace gases, they can put imagers on the aircraft to take pictures of things, look at smoke plumes and big storms and all kinds of interesting things. So the idea there is if we can fit a small radar onto that aircraft, then it can allow that aircraft to then go and tackle new science questions that it couldn't tackle before. Most likely it'll be the top of thunderstorms, right? So the radar itself will be deployed on one of two aircraft, either the ER-2, which is a manned aircraft, has one pilot in there. It's basically an engine with wings. That's a really high altitude aircraft, gets up to 22 kilometers in the atmosphere. And with that, we can fly right over the top of a thunderstorm, a really strong thunderstorm. Most aircraft don't fly above it because they can just barely get above it, or they get too close to the dangerous parts of the storm that are generating all the turbulence, things at higher altitudes in the atmosphere. In this case, we can fly high enough above the storm and use the radar to sample the cloud from a distance. So we don't endanger the pilot or the aircraft, but we still can do make some observations that otherwise could not be obtained by most other systems. So the radar will enable us to look at things like cloud particles, the characteristics of cloud particles, whether you have snowflakes or whether they're big plates or needles or different types of aggregates. So you get little ice crystals that stick together and they form big chains and things, so we can detect those types of characteristics of the radar. More importantly in this case is, especially when you are interested in things like turbulence, you can measure the winds and the storms. And so the radar can have Doppler capabilities, so it can measure the motion of the particles as they move to and from the radar when we take an observation. And so we'll be able to look at the dynamics in the storms, all the motions that ultimately lead to turbulence, or can lead to things like the exchange of water between the troposphere and the stratosphere. So generally in the atmosphere, we live in the troposphere. Here, where it's very moist, the stratosphere is very, very dry. Several orders of magnitude smaller concentrations of water vapor than we have in the troposphere. So all it takes is a little storm to go up and hit the tropopause, which is the boundary between the troposphere and the stratosphere, and inject a little bit of water in the stratosphere, and can have all kinds of impacts. It can change the chemistry in the stratosphere, it can lead to things like ozone destruction if there's enough water there. It can ultimately impact the radiation budget, so it can add to the warming that we get from trace gases like CO2 in the atmosphere. So when we talk about climate change, we typically talk about carbon dioxide, methane, all these greenhouse gases. Well, water is also a greenhouse gas, and it's very, very powerful greenhouse gas, and only takes a small push in the stratosphere from a storm or other impacts to ultimately have an effect on climate. So we're interested in all kinds of things happening at the tops of these storms, and we can sample that with the radar. We were supposed to start this in January, February this year if we did get approval at that point in time, or awarded the support to do this. Ultimately, we didn't find out until a little over a month ago, so we're a little late in getting started. I'm not sure the money has actually arrived here yet. But it should be here any time now. I haven't seen a notification yet, but from start of building the radar, designing to completion, ready for deployment to go put on an aircraft is 18 months. So that's really the main project period. But then as soon as the radar is developed, we'll go and we'll actually have an opportunity to fly this. And that's where when we take these observations, they will be on board a NASA aircraft. We'll get some observations, and the meteorology students and the engineering students will all get a chance to analyze this data. Ultimately, that could extend the project beyond that 18-month development and testing period and planning period on the meteorology side to something more like 2 years, maybe a little bit longer. And it just depends on when we're able to actually fly the instrument on NASA aircraft. And that ultimately will impact what types of science questions we ask and we address with the instrument. Whether it's really, strong thunderstorms, or it has to be something at another time of the year. If we're looking in the wintertime, we're not going to be able to investigate those types of storms, really strong severe storms, or summertime thunderstorms, very deep storms. We won't be able to investigate those as well. But the radar development, design, development, and integration will take place in the 18-month period. While the engineers are working on the radar side, the meteorology students will have an opportunity to see some of that and participate in some of those activities. But their primary job will be identifying science questions that we can answer with this. So that's another element of this. We're not only relying on the undergraduates to design and develop and ultimately deploy this instrument. We're also relying on undergraduates to design the science questions that we're going to be asking. So normally, again, you'll have a senior scientist or someone with a much longer history in the field, expertise in one of these areas, really designing these projects and carrying them out with a group of colleagues and other scientists from around the world with support of NASA or NSF or another one of these programs. But in this case, it's really the undergraduates really working with the vast amount of literature we have, talking with lots of people, like myself and other faculty here in the School of Meteorology, faculty in the engineering school or in other colleges on campus and departments, and really identifying some key science questions that we can say, hey, we've got this fantastic instrument that we're building, this really tiny radar to put on an aircraft. We'd like to do some science with that instrument, and what's really going to have an impact? What's a relevant science question that will ultimately benefit the larger scientific community, benefit NASA, benefit the university as a whole and our strengths and abilities that we have for future research with both undergraduate students and other faculty and graduate students here in the school and colleagues elsewhere. But ultimately, really, to have an impact on the science and to move our understanding and our knowledge forward. And that's ultimately what we want to do anytime we carry out one of these projects. But in this case, it's really the undergraduates taking the reins and establishing that leadership with a fair amount of mentoring from other experts and faculty here in the university. A number of things where this could ultimately benefit society by taking these observations. First and foremost, we're talking about motions and things at the tops of clouds. There are a couple questions. One, we don't really understand turbulence very well. We know it happens, and we know the types of processes that can lead to turbulence, but we don't have a really strong handle on why turbulence occurs in certain regions around a storm and not others for particular storms. In some cases it can be on one side of the storm. Another storm that looks very similar can be on the opposite side of the storm. It could be more above the storm or below the storm, depending on how the storm introduces different types of emotions in the atmosphere through waves. Just like you get waves and ripples in a pond, you get waves and ripples in the atmosphere when you have a storm that goes up and turns things up and generates all these waves. Well, ultimately, if we can understand turbulence better, we can better plan flights. So from the commercial side, if you're flying from LaGuardia to Denver or LaGuardia to Los Angeles or internationally, if you want to be flying anywhere, you have to know what predictions of turbulence are. If you can better understand turbulence in storms or just in the upper atmosphere in general, then we can better plan for these things and avoid those types of hazards with aircraft. So that's something where society could benefit. Another issue is it's really a current topic in the community, and it's not clear whether or not it's important. But if we look at storms that produce severe weather down here at the surface, there are a lot of interesting things that happen at the tops of these storms that we can detect from satellite. Well, one thing we can't do from satellite right now is look at the motions at the tops of these storms very well. Certainly not a lot of the waves and things that would lead to turbulence. But also, if we look at the storm top, it's not clear how motions at the top of the storm are connected to motions down near the surface. So if we have a storm that's rotating, that is able to produce a tornado down near the surface, is there similar rotation or related rotation? Is it connected at all to the processes happening lower down at the storm? Is there something similar happening up near the storm top? And that's not clear, and that's something that we could address with these observations. To study one of these storms that's producing severe weather and to look at the motions at the top and determine whether or not we can use that information to better prepare for hazards down near the surface. So if we see a storm that goes up, has a certain type of rotation or dynamic signature to it, we can say, hey, this storm's going to produce severe weather in X amount of minutes. And because today with aircraft and satellites, we can get updates on storms more rapid than we can get with current capabilities on the ground from radars, that maybe we can increase the amount of lead time that we get for some of these storms. So that's another way that we can benefit society with this work. So ultimately, if we understand the processes, then we can better prepare for them. And in addition, if we understand the processes, we can better represent those in numerical models, which we use to forecast the weather. So if we get better forecasts of the weather, that ultimately will impact everyone, whether they're down here at the surface or you're an aviation engineer telling people where they need to fly, and or forecaster, planner, flight planner.